In section 4.1, we're going to look at using the first and the second derivative to analyze a function. So we're going to interpret the sign of the first and second derivative. We're going to learn what critical points are and find them. And we're going to apply the first and second derivative tests to test the critical points to test for local extrema. Then we're going to find inflection points in a similar manner. So first we have a bunch of different definitions to go through. We have a local maximum is a function value that is the largest amongst those surrounding it. It is a maximum, is going to be a top of a hill. That's going to be the maximum. A local minimum is going to be the bottom of a valley, or at least commonly will be. Then we have two terms, the global maximum or absolute maximum and global minimum or absolute minimum is very similar to local max and local min, except that it is the largest function value or the smallest function value, I should say there. So what this means is we think about global means everything in our world. So for instance, the global maximum of elevation on our world is Mount Everest, but the local maximum or a local maximum may be the highest point in Rhode Island or something in a local area. Then we have this term that brings it all together. A local extrema is a local minimum or maximum. So extrema just means min or max, and global extrema means global min or global max. There's one other kind of detail we have to get through with these terms, and that is all of these terms represent y values. They are the function values, are the actual maximum and minimum. But that's really not even the information that we care about the most. We care about where it occurs more than what the actual value is. So we're going to say that f has a global maximum of 7 at x equals 4, if that were the case. And that means that the largest function value is 7 in the whole function, and that would correspond to the point 4 comma 7, or f of 4 equals 7. Now, sometimes we can kind of get away with saying the global max is 4, 7, like is the point itself, and that's going to be okay, but just know that there is a distinction between the y and the x values, and we'll be focused almost entirely on the x values, as that's going to help us determine the shape of our function. So let's look at an example and identify the local and global extrema in this picture. So note that we are assuming that this function continues off forever in the left-hand side, and it stops on the right-hand side, so it doesn't go any further there. So we could say the domain of this function is negative infinity to 3, or including 3. So let's identify here the local extrema. Let's do the local min first, or local mins, as there may be more than one. So local mins are going to be the bottom of valleys, or points where everything around it is bigger than that value. And note that that endpoint at 3 is also a local min. So we have local mins at x equals, that looks like negative 1.5, right about there. X equals 1 and x equals 3. These are negative 1.5, 1, and 3. Then we have local maxes, or maxima, at. We have a little top of a mountain there, a little top of a mountain there. But when we look at that left-hand side, there is no biggest function value. There's a biggest function value on the graph that I drew, but it keeps on going up forever. So these are the only two local maximum, and they occur at about x equals 0.5-ish and 2.1. I don't know. I'm kind of making up some values there. That's not really the point of this problem to be super exact. So then we think about what is the global min and global max. So the global min is the lowest function value, and that's going to be that guy down there, the very bottom of that big valley, and that's going to occur at the x equals negative 1.5. So that point is both a global min and a local min. And then we have, finally, the global max would be the largest function value for this function, and in this case, this does not exist. There is no biggest function value in this function. And that's going to occur with some functions. We're going to have some that do have global maxes, some that do not, and that's actually going to be one of the big things we have to get around in the next few sections is what do we do when we don't know if there's a global min or global max? How do we find it? We'll discuss that in the next couple sections. All right, so now let's talk about how can we find these values algebraically. And that's going to lead us into critical points. So a critical point of a function f of x is an x value c. So a critical point is a value c, it's an x value, such that the derivative is 0 or the derivative does not exist. So said other words, how do we find critical points? We find the derivative of the function, set it equal to 0, and find where the derivative does not exist. And those are going to be the critical points of the function. So when we're thinking about critical points, there's kind of two things we need to really understand. One is every local and global extrema occurs at a critical point. And that's because if we think about the top of a mountain or the bottom of a valley, the local max there has a horizontal tangent line. The derivative is going to be 0 at that point. And the same thing for the local min. Has a horizontal tangent line. But it goes further than that as well. We saw on the previous page we had a bit of a function that was the endpoint, and that was a local min. Let's draw it as a local max over here. So that could be a local max just as an endpoint. And note that the derivative does not exist at that point. Right? We might also have something like the absolute value function, and note that the derivative doesn't exist at this point. We'll say here. So we can maybe convince ourselves that it's going to be the points that have a horizontal tangent line, that means derivative equals 0, or where the derivative doesn't exist, that's where local or global extrema are going to occur. The next important fact there is that not every critical point is associated with a local or global extrema. Sometimes we get into this habit that global extrema and critical points, they are interchangeable, and that's going to be the case for a lot of problems that we deal with, but it is definitely not the case always. And a quick example is to look at x cubed. So let's think about finding the critical points of x cubed. We find the derivative, which is 3x squared, and we set it equal to 0. And that's going to give us one value of x equals 0. But note that when we look at the graph of x cubed, that is neither a min nor a max. That's something else entirely, right? But it still has a horizontal tangent line. So we're going to have to be careful that when we find critical points, we can't immediately assume that they're mins or maxes. We have to do a little bit of work to classify those points as mins or maxes or something else. In this case, this point is special. It's going to be known as an inflection point, and we'll talk about that in a few slides. So let's do an example to make sure we understand what we're doing here. Find the critical points, and maybe there's more than one, of f of x equals x cubed minus 6x squared plus 9x. So to find the critical points, we're going to find the derivative of the function. In this case, the derivative is 3x squared minus 12x plus 9, using the power rule a couple times. And to find the critical points, we are going to set our derivative equal to 0. So that's going to be 3x squared minus 12x plus 9 equals 0. Note that we can factor out a 3 from each term. So x squared minus 4x plus 3 equals 0. We can divide by that 3 or just write it as x minus 3, x minus 1 equals 0. So that's going to give us 2 points, x equals 3 and x equals 1. We also are going to check every time if the derivative does not exist at any point. In this case, since it's a polynomial, then there's nothing there, right? It exists everywhere. There's no weird points, so we don't have to deal with it. We'll see an example in the next video where we will have to kind of consider where the derivative doesn't exist. So our critical points are just x equals 1 and 3. We're going to revisit this example a couple times as we introduce our tests on the next couple pages. So we know there's critical points, but we don't know for sure if they are associated with mins or maxes or maybe something else entirely. So we need to have some kind of test to test whether these things are going to be mins or maxes or neither. The first one we're going to have is called the first derivative test, and it is named such not because it's going to be the first of 2 derivative tests. It is the first derivative test, the f prime test instead of f double prime. So if we know that c is a critical point of f, that means, or with the special case that f prime of c equals 0, this doesn't work if the derivative doesn't exist. But if the derivative is 0 at that point, then one of 2 things might happen. If the derivative is less than 0 before c and greater than 0 after c, so what does that mean? That means that before we get to c, this means that f is decreasing, and then afterwards, it is increasing. So let's think about that. We have some value c, and we know the function is decreasing, and then it is increasing after. That means that this is going to be a local min. So the idea is we look at the sign of the derivative to the left and the right of c. Now we're going to do the exact same thing if it's the other way around. If it's increasing before and decreasing after, then we look at our value c. We think that it's going to increase before, decrease after. That is going to be a local maximum. All right, so let's apply the first derivative test to our example. Note that we had that the derivative was 3x squared minus 12x plus 9. And actually, I'm going to write that in the factored form, as that's going to be easier to deal with. 3x minus 1, x minus 3. And we had our 2 critical points of 1 and 3. So I think the easiest way to go about the first derivative test is to look at a little number line. We're going to label our critical points 1 and 3. And we are going to test the sign in each region that is bordered by a critical point. So here I'm going to put some dotted lines here. Actually, I'm not going to do that because that means something else a little bit later. But we have kind of like 3 regions. We have this region before 1, this region in between 1 and 3, and this region after 3. And we know that in these regions, the derivative has to be either all positive or all negative. And this is similar to things that you've done in pre-calc when we had to draw rational functions or polynomial functions. So why is it true that in each of these regions, the derivative has to be all positive or all negative? And note that we are looking at the derivative here. It is because that if it would change from positive to negative, then one of 2 things would have to happen. It would either have to cross the x-axis, and that means that that has to happen when the derivative is equal to 0, but we've already labeled all points where that occurs, or there would have to be some kind of discontinuity where we have a jump over the x-axis or some kind of vertical asymptote or something weird going on. And that would be another critical point because that would be a point where the derivative does not exist. So, all being said, in each of these 3 regions, we're going to have all positive or all negative points in the derivative. We just need to test one of them to test if it's positive or negative. So we are going to test points in each region. So let's look at a point in the first region. I think the easiest point to pick is maybe 0. So if we look at the sign of the derivative, f prime of 0, we're going to plug that into the factored form as that's going to be easiest to think about the sign. 3 times 0 minus 1 times 0 minus 3 is going to be a negative number times a negative number. That's going to be a positive number. So in that entire region, the derivative is going to be positive. Next, let's think about in between 1 and 3. Let's just pick 2. That seems nice. F prime of 2 is going to be 3 times 2 minus 1, 2 minus 3 is going to be a positive number times a negative number, which is a negative number. I don't even care what the numbers are. All I care about is if it's positive or negative. And then lastly, let's do the third region. Let's pick 10 for no reason, other than it's greater than 3. 3 times 10 minus 1. 10 minus 3 is a positive number times a positive number. That's all positive. And there we go. So what does this derivative actually look like? This derivative is going to look something like, here's 1, here's 3. It is going to cross the x-axis at those points and then go up in either direction. We don't really need to know what the exact shape of it is, just the sign. All right, so now that we've done the testing of the points, we have our little chart here. Let's classify the critical points. So by the first derivative test, x equals 1 is going to give us a local maximum. And that is because the derivative is increasing before, or the derivative is positive before and negative after. The function is increasing before and decreasing after. And then x equals 3 will be a local min, as it is decreasing before, increasing after. The derivative is negative before, positive after. So this testing point kind of idea is something that we've seen in pre-calc before, and it really is the same thing that we're doing now to look at the shape of the derivative and whether it's positive or negative. We have another test that we can use. This is called the second derivative test. And note that it's not called second derivative test because it is our second test that involves derivatives. It involves the second derivatives. That's why it's called the second derivative test. And why do we have this? And that's because the first derivative test is not always easy to do. You have a lot of critical points. You have a difficult derivative to deal with. It's a lot of plugging in points, and it can be time consuming. The second derivative test will often be much quicker if we can find the second derivative, but it won't always work. We have to be kind of careful of that. So same setup. If we have C a critical point of f of x, that is f prime of c equals 0, it's not going to work if the derivative doesn't exist. Then if the second derivative is positive, then f has a local min at x equals c. If the second derivative is negative at that point, then f has a local max at x equals c. And if the second derivative is equal to 0 at that point, then the test does not work. It's inconclusive. We can't say one way or the other whether it's a min, a max, or something else. So this may seem backwards, right? We have a positive second derivative and we have minimum, and those things kind of seem backwards, but let's think about what this means. Positive second derivative means that our function is concave up. So let's draw a concave up function, and we can see that on that little smiley face portion, the bottom of that is a local min. So this is saying that if you know the derivative is 0 at a point, if you know it's going to be the bottom of a valley or a top of a mountain, and you can say that it's going to be concave up at that point, it has to be the bottom of a valley. Likewise, if we have f being concave down, we have a big frowny face, and we should have the top of a mountain be the local maximum. And it is true that if the second derivative is equal to 0, that just means that it does not work and you can't use that test. At that point, you should try the first derivative test to classify that critical point. So let's see the second derivative test in action and see how it can be much quicker for a problem like this. Note that we have the derivative here was 3x squared minus 12x plus 9, and we had critical points 1 and 3. So the second derivative test says, take the second derivative. In this case, it's going to be 6x minus 12, and we are going to test plugging in those critical points into the second derivative. In this case, we have 6 times 1 minus 12. That is less than 0. That's a negative number. So therefore, at x equals 1, we have a local max, as it's going to be a concave down function at that point. When we plug in 3, we have 6 times 3 minus 12. All I care is that that is greater than 0. And therefore, we have at x equals 3, we have a local min. Positive second derivative would be a local min. And both those tests that we did, first derivative test, second derivative test, both work, and they both give us the same information for this example. Why do we have two different tests? One is quicker usually and will be nice, but doesn't always work. One is a little slower, but it will always work. So then our last little topic here is the idea of inflection points. So an inflection point is going to be very similar to what's going on with critical points of the function, except now we're looking at critical points of the derivative. That is looking at when the second derivative is 0. So an inflection point is a point P, an x value P, in which the second derivative of P is equal to 0, and the sign of f double prime changes at P, that means that the function changes concavity. And that's really what an inflection point is. It's a point where the concavity changes. So every inflection point is going to occur when f double prime equals 0. This is the same thing we said with critical points. Every inflection point occurs when f double prime equals 0. However, not every point where f double prime equals 0 is an inflection point. So let's look at our two examples, x cubed and x to the fourth. Here, x equals 0 is an inflection point. And what's changing at this point? Well, the function changes from concave down to concave up. And we know the second derivative is 0. We can say f prime of x is equal to 3x squared. F double prime of x is equal to 6x. Right, when we set that equal to 0, we get x equals 0. So in this case, x equals 0 is an inflection point. However, if we look at the next example, we have the derivative is 4x cubed. The second derivative is 12x squared. When you set that equal to 0, you get x equals 0 again. But the concavity is not changing. In this case, we have concave down everywhere. So the concavity is not changing. So x equals 0 is not an inflection point. It's something else. In this case, it is a local minimum, not an inflection point. So bringing it all together, let's think about what we've kind of learned in this video and try to make some connections to things we may have known before. So there is a big relationship between the function and its derivative and its second derivative. We talked about when a function has a positive derivative, that means that the function is increasing. We have a positive second derivative, the function is concave up. And now we're going to think about when does it equal 0. So something that we didn't say in this video yet, but is true, we know that the function itself changes sign at x-intercepts. And these are the points where f of x equals 0. This is something that you learn in algebra. When you have a function cross the x-axis, right, we go from f being positive to f being negative. And that special point where it does that is going to be an x-intercept. So when we think about the derivative, when the derivative changes signs, that's going to be at a local extrema. That means that we have the function is increasing, and then it changes to decreasing, or vice versa, and that's going to be at a local extrema, in this case, a maximum, what I drew. Right, so this is f prime greater than 0, f prime less than 0. Here's a local max. And an inflection point is where we change from maybe concave up to concave down. And this special point where that happens is called an inflection point. We go from the second derivative being positive to the second derivative being negative. So there's something special about the change of sign in the function, its derivative, and its second derivative. But we need to know that just because the derivative or the second derivative equals 0 does not mean that the corresponding function is changing sign. It doesn't mean that we have a local extrema or an inflection point. It would mean that we have an x-intercept, but it doesn't mean that it has to change sign. So for instance, if we think about this little guy here, when the function is equal to 0, we don't have to change sign, but it can still be an x-intercept. And that's kind of the analog we're using for the derivative being 0 or second derivative being 0, but not having a local extrema or not having inflection points. So looking at the signs of the function and the derivative allows us to understand the shape of the function fully. And we'll go over a couple example problems in the next video where the goal is just to sketch the function. Use the information from the derivative and second derivative to sketch the function fully.